To determine the required secondary feeders, the National Electrical Code, or NEC, mandates consideration of several factors. Firstly, the transformer kilovolt ampere rating, secondly, the overcurrent protection device rating, and thirdly, voltage drop limitations. Let's begin by determining the feeder current. The formula for calculating feeder current is feeder current equals overcurrent protection device rating divided by the square root of 3 multiplied by the nominal voltage. In our scenario, the overcurrent protection device rating is 150 amps. The square root of 3, used for a 3-phase system, is approximately 1.732. The nominal voltage is 208 volts. Plugging these values into the formula, we get feeder current equals 150 amps divided by 1.732 multiplied by 208 volts, which equals 128.2 amps. Now, let's determine the required feeder size. The required feeder size is determined based on the feeder current and the NEC requirements for voltage drop. For a 3-phase 208Y/120 volt system, the maximum allowable voltage drop is 3%. Using a wire size table that considers the voltage drop, the required feeder size for a current of 128.2 amps is AWG1/0. Therefore, the required secondary feeders for the 45 kV ampere K13 transformer with a 150 amps overcurrent protection device in the 208Y/120 volts panelboard are AWG1/0. It's crucial to understand the underlying principles and calculations involved in sizing transformer secondary feeders. Adhering to NEC guidelines ensures electrical safety and code compliance. The NEC provides tables and guidelines for selecting appropriate wire sizes based on ampacity and voltage drop considerations. Ampacity refers to the current carrying capacity of a conductor, while voltage drop is the reduction in voltage along the length of the conductor due to its impedance. The NEC specifies maximum allowable voltage drop to ensure proper equipment operation and prevent overheating. When sizing transformer secondary feeders, it is important to consider the following factors. Firstly, the transformer's kilovolt ampere rating. This determines the amount of power that the transformer can supply, and consequently the maximum current that the secondary feeders must be able to carry. Secondly, the overcurrent protection device rating. The overcurrent protection device, such as a circuit breaker or fuse, protects the transformer and the secondary feeders from overloads and short circuits. The feeder conductors must be sized to carry at least the rating of the overcurrent protection device. Thirdly, the ambient temperature. The ampacity of a conductor decreases as the ambient temperature increases. Therefore, it is important to consider the ambient temperature when selecting the appropriate wire size. Fourthly, the number of conductors in a raceway or cable. When multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be derated. This is because the heat generated by each conductor can raise the temperature of the other conductors, reducing their ampacity. Fifthly, the distance from the transformer to the load. The longer the distance from the transformer to the load, the greater the voltage drop in the conductors. Therefore, it is important to consider the distance when selecting the appropriate wire size. To accurately size transformer secondary feeders, you need to follow a systematic approach. Here's a breakdown of the key steps involved. Firstly, determine the transformer's secondary voltage and current. This information is typically found on the transformer's nameplate. For instance, in a 208Y/120 volt system, the secondary voltage is 208 volts for line-to-line connections and 120 volts for line-to-neutral connections. Calculate the secondary current using the formula kilovolt amperes multiplied by 1000 divided by the product of the square root of 3 and the secondary voltage for 3-phase systems. Secondly, determine the overcurrent protection device rating. The overcurrent protection device, typically a circuit breaker or fuse, should be sized to protect the transformer and the secondary feeders from overloads and short circuits. The NEC provides guidelines for selecting the appropriate overcurrent protection device rating based on the transformer's kilovolt ampere rating and secondary voltage. Thirdly, calculate the minimum required ampacity of the secondary feeders. The secondary feeders must be sized to carry at least 125% of the continuous load plus 100% of the non-continuous load. This ensures that the feeders can handle the expected load without overheating or causing excessive voltage drop. Fourthly, select the appropriate wire size based on the calculated ampacity and the NEC ampacity tables. The NEC provides ampacity tables that list the allowable ampacities for various wire sizes and insulation types. Select a wire size that has an ampacity equal to or greater than the calculated minimum required ampacity. Fifthly, check for voltage drop. Voltage drop is the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or not operate properly. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Use voltage drop calculators or tables to determine the voltage drop for the selected wire size and conductor length. If the voltage drop exceeds the recommended limits, increase the wire size until the voltage drop is within acceptable limits. Sixthly, consider ambient temperature and conductor dirting. The ampacity of a conductor decreases as the ambient temperature increases. If the conductors are installed in an area with a high ambient temperature, you may need to direct the ampacity of the conductors. The NEC provides tables for dirting conductors based on ambient temperature. Additionally, if multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be directed. The NEC provides tables for directing conductors based on the number of conductors in a raceway or cable. Seventhly, install the secondary feeders in accordance with the NEC requirements. The NEC provides detailed requirements for installing conductors, including requirements for raceways, cable types, and conductor spacing. Ensure that the secondary feeders are installed in accordance with all applicable NEC requirements. When working with electrical systems, safety is paramount. Always follow these safety precautions to prevent electrical shock and other hazards. Firstly, de-energize the circuit before working on any electrical equipment. Turn off the power at the circuit breaker or disconnect switch and verify that the circuit is de-energized using a voltage tester. Secondly, wear appropriate personal protective equipment, or PPE. Wear safety glasses, gloves, and other appropriate PPE to protect yourself from electrical shock and other hazards. Thirdly, use insulated tools. Use insulated tools that are rated for the voltage you are working with. Fourthly, follow lockout/tagout procedures. If you are working on a circuit that could be energized by someone else, follow lockout/tagout procedures to prevent the circuit from being accidentally energized. Fifthly, be aware of your surroundings. Be aware of your surroundings and avoid contact with any conductive surfaces. Sixthly, if you are not qualified to work on electrical equipment, do not attempt to do so. Hire a qualified electrician to perform the work. Transformers play a critical role in electrical power distribution systems. They are used to step up or step down voltage levels to efficiently transmit and distribute electricity. Understanding transformer characteristics and operation is essential for electrical engineers and technicians. Transformers operate on the principle of electromagnetic induction. A transformer consists of two or more coils of wire, cold windings, that are electrically isolated but magnetically linked. The primary winding is connected to the source voltage, and the secondary winding is connected to the load. When an alternating current flows through the primary winding, it creates a magnetic field that induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. Transformers are typically rated in kilovolt amperes, which represents the apparent power that the transformer can deliver. The kilovolt ampere rating is determined by the transformer's design and its ability to dissipate heat. The K rating of a transformer indicates its ability to withstand harmonic currents. Harmonic currents are non-sinusoidal currents that can cause excessive heating in transformers and other electrical equipment. Transformers with a higher K rating are better able to withstand harmonic currents without overheating. Voltage drop is an important consideration in electrical power distribution systems. Excessive voltage drop can cause equipment to malfunction or not operate properly. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Voltage drop is caused by the resistance of the conductors in the circuit. The longer the conductor and the smaller the conductor size, the greater the voltage drop. To minimize voltage drop, use larger conductors and keep conductor lengths as short as possible. The NEC provides guidelines for calculating voltage drop and selecting the appropriate conductor size. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical wiring and equipment in the United States. The NEC is updated every 3 years to reflect changes in technology and safety practices. The NEC is not a law, but it is widely adopted by state and local governments. Compliance with the NEC is essential for ensuring electrical safety and preventing fires. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important for electrical engineers, technicians, and contractors to be familiar with the NEC requirements. Grounding is an essential safety measure in electrical power distribution systems. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and energize the circuit. This protects people from electrical shock and prevents equipment damage. The NEC provides detailed requirements for grounding electrical systems. Overcurrent protection is another essential safety measure in electrical power distribution systems. Overcurrent protection devices, such as circuit breakers and fuses, protect circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the rated capacity of the conductors. Short circuits occur when there is an unintended connection between two conductors. Overcurrent protection devices are designed to trip and energize the circuit when an overload or short circuit occurs. The NEC provides guidelines for selecting the appropriate overcurrent protection device for a given circuit. Electrical safety is paramount when working with electrical systems. Always follow safe work practices and use appropriate personal protective equipment. If you are not qualified to work on electrical equipment, do not attempt to do so. Hire a qualified electrician to perform the work. Always to energize circuits before working on them. Use insulated tools and wear appropriate personal protective equipment. Be aware of your surroundings and avoid contact with any conductive surfaces. By following these safety precautions, you can prevent electrical shock and other hazards. Calculating the correct feeder size involves a few steps that are crucial for ensuring safety and code compliance. Firstly, determine the transformer's secondary current. The secondary current can be calculated using the formula I = S divided by V, where I is the current in amps, S is the apparent power in volts amperes, and V is the voltage in volts. For a three-phase transformer, the formula is adjusted to I = S divided by the square root of 3 times V. Secondly, apply NEC guidelines for continuous and non-continuous loads. According to the NEC, feeders must be sized to carry not less than 125% of the continuous load, plus 100% of the non-continuous load. Continuous loads are those that operate for 3 hours or more at a time. Non-continuous loads are those that operate for less than 3 hours at a time. Thirdly, select appropriate conductors based on ampacity. After determining the required ampacity, refer to NEC Table 310.16, which provides the allowable ampacities for insulated conductors rated up to 2000 volts, based on the insulation type and temperature rating. Choose a conductor size that has an ampacity equal to or greater than the calculated load current. Fourthly, consider voltage drop limitations. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Voltage drop can be calculated using various formulas or online calculators. If the voltage drop exceeds the recommended limits, increase the conductor size to reduce the voltage drop. Fifthly, apply correction and derating factors. The allowable ampacity of conductors must be corrected for ambient temperature and derated for the number of conductors in a raceway or cable. NEC Table 310.15b2 provides adjustment factors for ambient temperature, and NEC Table 310.15b3 provides adjustment factors for the number of conductors in a raceway or cable. Apply these factors to the allowable ampacity to determine the adjusted ampacity. Sixthly, select overcurrent protection. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductors from overloads and short circuits. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the conductor ampacity. The overcurrent protection device should not exceed the conductor ampacity unless certain exceptions apply. The K-factor is a measure of a transformer's ability to withstand harmonic currents without overheating. Transformers that supply nonlinear loads, such as electronic equipment, are subject to harmonic currents. These harmonic currents can cause excessive heating in the transformer, which can reduce its lifespan and increase the risk of failure. K-rated transformers are designed to mitigate the effects of harmonic currents. They have a higher capacity to dissipate heat and are less susceptible to overheating. The K-factor indicates the level of harmonic current that the transformer can withstand. A higher K-factor indicates a greater ability to withstand harmonic currents. When selecting a transformer for a nonlinear load, it is important to choose a transformer with a K-factor that is appropriate for the level of harmonic current that is expected. The NEC provides guidelines for selecting K-rated transformers.